So this is indeed the general idea of the expectation maximization, or EM algorithm. So in all the EM algorithms, we introduce a hidden variable to help us solve the problem more easily. In our case, the hidden variable is a binary variable for each occurrence of a word. And this binary variable would indicate whether the word has been generated from theta sub d or theta sub b. And here we show some possible values of these variables. For example, for the, it's from background, the z value is 1. And text, on the other hand, is from the topic, then it's 0 for z, etc. Now, of course, we don't observe these z values. We just imagine there are such associated values of z attached to all the words. And that's why we call these hidden variables. Now, the idea that we talked about before for predicting the word distribution that has been used to generate the word is to predict this, the value of this hidden variable. And so the algorithm, the EM algorithm then would work as follows. First, we'll initialize all the parameters with random values. In our case, the parameters are mainly the probability of a word given by theta sub d. So this is the initialization stage. These initialized values would allow us to use Bayes' rule to take a guess of these z values. So we'll guess these values. We can't say for sure whether text is from background or not, but we can have our guess. This is given by this formula. It's called an E step. And so the algorithm would then try to use the E step to guess these z values. After that, it would then invoke another step called M step. In this step, we simply take advantage of the inferred z values and then just group words that are in the same distribution, like these, from background, including this as well. And we can then normalize the count to estimate the probabilities, or to revise our estimate of the parameters. So let me also illustrate. We can group the words that are believed to have come from theta sub d, and that's text mining algorithm, for example, and clustering. And we can group them together to help us re-estimate the parameters that we're interested in. So these will help us re-estimate these parameters. Note that before we just set these parameter values randomly, but with this guess, we will have a somewhat improved estimate of this. Of course, we don't know exactly whether it's 0 or 1, so we are not going to really do the split in a hard way, but rather we're going to do a soft split, and this is what happened here. Right? So we're going to adjust the count by the probability that we believe this word has been generated by using the theta sub d. And you can see this, where does this come from? Well, this has come from here, right? From the E step. So the EM algorithm would iteratively improve our initial estimate of parameters by using E step first and then M step. The E step is to augment the data with additional information like Z. And the M step is to take advantage of the additional information to separate the data, to split the data counts, and then collect the right data counts to re-estimate our parameters. And then once we have a new generation of parameters, we're going to repeat this. We're going to use the E step again to improve our estimate of the hidden variables. And then that would lead to another generation of re-estimated parameters for the word distribution that we're interested in. Okay, so as I said, the bridge between the two is really the variable z, hidden variable, which indicates how likely this word is from the topic word distribution theta sub d. So this slide has a lot of content, and you may need to pause the video to digest it. But this basically captures the essence of EM algorithm. start with initial values that are often randomly set, and then we invoke E step followed by M step to get an improved setting of parameters. And then we repeat this. So this is a hill climbing algorithm that would gradually improve the estimate of parameters. And as I will explain later, there's some guarantee for reaching a local maximum of the likelihood function. So let's take a look at the computation for a specific case. So these formulas are the EM formulas that you see before. And you can also see there are superscripts here, like here, N, to indicate the generation of parameters. Like here, for example, we have N plus 1. That means we have improved parameters. So from here to here, we have improvement. So in this setting, we have assumed the two models have equal probabilities and the background model is known. So what are the relevant statistics? Well, these are the word counts. So assume we have just 4 words and their counts are like this. And this is our background model that assigns high probabilities to common words like the. And in the first iteration, you can picture what would happen. Well, first we initialize all the values. So here, this probability that we're interested in is normalized into a uniform distribution over all the words. And then the E step would give us a guess of the distribution that has been used to generate each word. We can see we have different probabilities for different words. Why? Well, that's because these words have different probabilities in the background. So even though the two distributions are equally likely, and then our initialization says uniform distribution, because of the difference in the background word distribution, we have different guessed probabilities. So these words are believed to be more likely from the topic. Right? These, on the other hand, are less likely probably from background. Right? So once we have these Z values, we know in the M step, these probabilities would be used to adjust the counts. So 4 must be multiplied by this 0.33 in order to get the allocated counts toward the topic. And this is done by this multiplication. Note that if our guess says this is 100%, if this is 1.0, then we just get the full count of this word for this topic. But in general, as I said, it's not going to be 1.0. So we're going to just get some percentage of the counts toward this topic. And then we simply normalize these counts to have a new generation of parameter estimate. So you can see, compare this with the old one, which is here, right? So compare this with this one, and we'll see the probability is different. Not only that, we also see some words that are believed to have come from the topic will have a higher probability, like this one, text. And of course, this new generation of parameters would allow us to further adjust the inferred latent variable or hidden variable values. So we have a new generation of values because of the E step based on the new generation of parameters. And these new inferred values of these will give us then another generation of the estimate of probabilities of the words, and so on and so forth. So this is what would actually happen when we compute these probabilities using the EM algorithm. And as you can see in the last rule, where we showed the log likelihood, and the likelihood is increasing as we do the iteration. And note that this log likelihood is negative because the probability is between 0 and 1. When you take logarithm, it becomes a negative value. Now what's also interesting is to note the last column, and these are the inferred word split, and these are the probabilities that a word is believed to have come from one distribution, in this case the topical distribution, right? And you might wonder whether this would be also useful, because our main goal is to estimate these word distribution, right? So this is our primary goal. We hope to have a more discriminative word distribution, but the last column is also a byproduct, and this actually can also be very useful. And you can think about that. And one use is to, for example, estimate to what extent that this document has covered background words. And this, when we add this up or take the average, we will kind of know to what extent it has covered background versus content words that are not explained well by the background.